Okay, we are recording. Uh, let's put this back away. You like my first slide? Yeah. Okay, so visible light communications. So just a little background. I found out about this a number of years ago when Clint and Gordon first came up with this crazy idea to do visual light communications and went out and tried it. And I was reading on the website and found all kinds of great information. I thought, that's a really cool topic. And then I immediately forgot it and moved on to other things. And it just came up again when Gordon passed away. And I was like, oh, I should do a class on that. That would actually be kind of interesting. And it's different. It's not what we're used to, right? So yeah, my first slide is what? And I'll warn you up front, there's going to be some slides with like a wall of text that I'm going to sit here and read to you. So be advised, you will be very tired of the melodious tones of my voice by the time we finish. But yeah, so ham radio is about radio. What are we talking about? Visible light. What's this nonsense? What is visible light? Well, visible light is electromagnetic radiation, and radio is electromagnetic radiation. So there's a little bit of a parallel there. What about the frequency? Well, you know how we talk about how we're typically on 2 meters, we're in the 144 to 148 megahertz. Well, visible light is up around 400 to 800 terahertz and has a wavelength of 400 nanometers to 635 nanometers. Nanometer is a billionth of a meter. So it's pretty darn small. So yeah, but it is electromagnetic radiation, just like our radio is. So if you look at the electromagnetic spectrum, you will see that it goes all the way from the low frequency radio waves through microwaves, infrared, visible light, ultraviolet, X-rays, and all the way up through gamma rays. And when we start talking about, how we talk sometimes about like DC to daylight. Have you guys ever heard that? When people are talking about a wide band receiver, a receiver that could pick up all the bands, we talk about DC to daylight, where DC is direct current, and that would be 0 hertz, right? It's just one solid line, and daylight is visible light, but it actually goes higher than that too. I mean, we don't do anything up there, but yeah, we actually could do some stuff up there. So is it legal? Well, interestingly enough, all modes and licensees except novices, any novices in the room? Yeah, I didn't think so. Except novices are authorized any amateur bands above 10.5 gigahertz, and all frequencies above 275 gigahertz are open to amateur radio operators. So if you look down here, I don't know if you can see my mouth moving around, but it says right here, all above 275 gigahertz. So anything above 275 gigahertz, trust me, terahertz are above gigahertz. Those are open to amateur radio operators. So yeah, it's actually legal for us to do this. All right, so let's have a little history lesson. Let's say it's the mid 1800s and you need to get a message from Salt Lake City to Denver, or Denver to Salt Lake City. What are your options? Obviously, you can write your message on a piece of paper, hand it to somebody who's going from Denver to Salt Lake City and say, give this to so-and-so when you get there. And a few weeks later, it may show up or may not, right? Alternately, you can build a series of towers with a contraption mounted on top that can be moved into different positions. And the towers can be some tens of miles apart. And you can hand your message to tower number 1, and that guy can set his contraption in particular orientations for each letter of your message. Meanwhile, a guy in the next tower is watching with a telescope or binoculars or something, and he's copying down your message. And then he turns around and does the same thing to the next tower in line. And over the course of a few hours, your message is delivered. Well, isn't that pretty cool? Did they really do that? Yeah, they did. This exact system is called the optical telegraph, was developed by the Chap brothers in 1792, believe it or not. That, when you think about that, that's well before any radio stuff ever happened, right? And they figured this out that, hey, you know what? If we make some patterns and we assign each letter to a pattern or each pattern to a letter, we can actually make patterns that are visible from a far distance. And by simply building several of these little stations across the place, we are able to move our messages around. And they built this in Europe. This was actually a thing that was done in Europe. I don't think it was ever done here in between Denver and Salt Lake, but it certainly could have been. So very, very interesting system. And you look at this and you look at some of the shapes and you're like, why in the world did they pick that shape for that letter? And ultimately what it came down to was they were trying to find shapes that were easily discernible from a distance. So that's why they chose the shapes they did. Now, why they assigned shapes to particular letters, I have no idea. But because I see like S and O, there's only one little difference here. Is it related to frequency of letters and how fast they can change the position of the thing? I don't think so. I think they just arbitrarily assigned them. But
Somebody said, let's use an F for C.
maybe, yeah. I mean, I don't know. I don't know what the plan was or what their thought process was when they assigned these shapes, but nevertheless, they assigned these particular shapes and they used this quite effectively in Europe. Later, some bright light bulb figured out that you could drag a wire from Denver to Salt Lake City and run an electric current down it. And when you turn the current on, you could make a little block of metal thump in one direction. And when you turned it off, it would thump in the other direction. And by adjusting how many times and how fast and how long those thumps happened, you could send some kind of information back and forth. And then you could come up with like sequences of those long and short thumps and maybe call them something like, I don't know, Morse code. And with that mechanism, you can send messages, even when the sun's not shining and you can't see the semaphore, right? So it was kind of a cool thing. Also, when you are running your signal down a wire, there was an advantage because your enemies couldn't see the signal going through the wire. Now, there was also a disadvantage, and that was that your enemies could cut the wire, right? So that was something to consider as well. But yeah, so we developed the telegraph because it was deemed to be more expedient. Now, the Navy found it difficult to string the wires between their ships because the ships were moving farther apart and closer together and things. Plus, there was a lot of water around, and dipping wires in water wasn't considered a real great idea. Later, they figured out that if they put the appropriate wrapping around the wires, they could actually put them under the water and run them from one continent to another. But that didn't happen initially, right? So what these guys did was they said, hey, if we have a bright spotlight and we point it at another ship, and then we rig up some kind of shutter in front of it that we can open and close, we can send Morse code using a beam of light. Pretty cool. They didn't want to just like turn the light on and off because these were typically arc lamps that once you lit them, you took great pains to keep them lit and keep them burning, including like adjusting the arc length and things like that in order to make sure that they stayed lit. And they took a while to get lit up, and they took a while to fade out when you shut them down. So, but yeah, the Navy guys, they were pretty smart on this. So that was a cool thing that they did. And they called this a telegraph system, right? This was an optical telegraph. Around 1880, this sharp dude named Alexander Graham Bell, he came up with this idea that, it would be really neat if you could just like talk into something on one end and then hear whatever was said over on the other end, right? And he thought this was totally cool. And so what he thought of was this thing that he called the photophone. And the idea was you take a beam of light and you shine it on a mirror or prism or something. And then as you shout into the tube, it makes that mirror vibrate. And that makes the beam of light vibrate. Meanwhile, on the other end, you have a photoreceptor that picks this up, and through, you know, some manipulation of electricity and use of some speakers, turns it back into an audio signal that you can listen to. And he thought this was amazing. He thought this was so, he patented this idea. He thought this was the totally coolest thing. He thought it was so cool, he wanted to name his second daughter Photophone. Fortunately for his daughter, his wife said no. But yeah, this was an actual thing, right? I didn't know about anything about the photophone before I started researching this talk. And you know, when I read that bit about his daughter, I was like, whew, dodged a bullet there. They ended up naming her something like Mirabelle or something like that. And I think they nicknamed her Daisy, which obviously works right well with photophone. It just kind of falls right off the lips. Surprisingly, the idea didn't take. The problem being, what if the sun wasn't shining? What if it wasn't shining in the right place? You had to very carefully aim your beam and everything and make sure that the people on the other end were listening when they needed to be and all that kind of stuff. So, but we're going to talk about some of those problems as we move on. But hey, if it worked for Alexander Graham Bell, I bet it would still work, which brings us to more modern times. We'll talk about Marconi and his wireless contraptions some other time. I you know, it's not really something that we talk about in this class, in this club here, but I'm sure we'll get around to it at some point. So let's talk about Operation Redline. So in 1963, this was the year before I was born. These guys who worked for a company called Electro-Optical Systems had a brand new gadget in their hands called the neon red laser. And they said to themselves, man, this is cool. I bet we could use it to communicate over some kind of distance. And so they figured out they wanted to do that. So the text here that I'm gonna sit here and read this because, well, you have to listen to me. So basically, this text is from an interview that was done with Bob Legg about the time of the experiments that we're going to talk about. Well, probably a few years before. But yeah, so in Bob's own words, he said, the company that we work for, Electro-Optical Systems in Pasadena, California, had a number of amateur radio operators in the company. And the thought among some of us was we should have an amateur radio club. So we had our first get together to talk about forming a club in late January '63. And the question at the time was, why have a club within the company when almost all of us have membership in one or more amateur radio clubs outside? And the consensus was, if we were going to form a club within the company, we needed to have some kind of a goal, like breaking some kind of record or contributing something scientifically new to the field of electronics. So we went away from that meeting thinking about this. And when we met a week later, we'd come up with a few ideas what we might want to do. It was decided, let's build a laser and see if we can't break the world record. The record wasn't very far at the time, about 35 miles, established by Hughes Aircraft. We finished the meeting having chosen some members to head up various tasks that were involved, such as laser construction, receiver construction, path selection, someone to be in charge of the receiver site and the laser site, and someone to be in charge of material acquisition. These people weren't hard to choose, as all but two of those who showed up at the meeting participated in the laser event. So among those who participated were Dr. Henry Richter, Dwayne Irway, Dave McGee, Jack Patterson, Bob Legg, Park Squires, who owned the telescope. That was a very handy gadget to have at that time, right? So he says, we were able to obtain a helium neon tube already fitted with Brewster windows on the ends used to maintain polarization. We were originally thinking of modulating this laser using a Kerr cell, which rotates polarization. But this idea was later abandoned due to the awkwardness and hazard of using a Kerr cell, which often contains nitrobenzene, a very hazardous substance, and the fact that the exciter itself could be modulated. We also obtained two mirror mounts with micrometer adjustments for alignment, and we installed confocal reflectors. The exciter and modulator was a Viking 2 made by Johnson, a very popular line of ham equipment at that time. I had a Viking 2, so I offered its use. We excited the laser at 28.62 megahertz in the 10-meter band, and by amplitude modulating the Viking, which put out about 100 watts of RF, we were able to excite the laser. We collimated the laser with a 10-power telescope with a 2-inch exit diameter and mounted the whole assembly, including a spotting scope, in a steel beam that was 12 inches wide, 4 inches deep, and 6 feet long. The most power we ever got out of the laser was 125 microwatts. The laser tube itself had no internal electrodes, requiring external RF excitation. Initially, we had no idea how to do this, but after some experimentation, we determined that applying RF to strips of foil properly placed on the outside of the tube did the job. Now, here's the interesting factor. Okay, so this Viking 2 unit drew 250 watts of power to operate, to produce 100 watts of output power. And that 100 watts of output power was used to excite the laser to produce, how much did he say? 125 microwatts of laser energy.
1/8 of a milliwatt.
1/8 of a milliwatt, right? So they figured out that it was like 0.0000005% efficient in what it was doing. But they got it to work. So, all right, he says, I'm sure we could have improved the output power with more experimenting, but there was an overwhelming urge to get into the field as fast as we could because we were aware there were at least 2 other groups that were about to break the current record, Ryan Aircraft in San Diego and the Army Signal Corps that was setting up a facility to break the record. And while they were out there pouring concrete for foundations, we were dragging this thing out, right? So they had it in their hands and figured instead of just leaving it on the workbench, we'll take it out there and do it while they're busy, pouring concrete like the Army likes to do. Parks's Newtonian telescope had its own mount and used a 12.5-inch mirror. For detection, we had available an S20 photomultiplier tube and a power supply for it. This is probably not the best choice of photomultiplier tubes, but it seemed to work and we had it available. That is to say, free. We also had an audio amplifier with a speaker and a tape recorder to document the event. The first tests were performed at EOS once the laser was up and running. Our building, which was only a few months old, was about 300 feet long, and we beamed our laser down the hall at night with a mirror at 3 corners. The beam went around the building from the south hallway to the north hallway to a separate room for the receiver. With neutral density filters that we'd hoped were equivalent to the path loss, we were able to get very good communications. What we didn't have were the scintillation effects, which about wiped us out. We're going to talk more about scintillation in a bit. The sites that we used were determined by Dave McGee and his team. They'd studied topographical maps for some time and field checked availability of the 2 sites that had been selected to meet our goal of 100 miles or so. The transmitter site was easy to get to with paved roads all the way to the Glassy Hollow campground in the San Gabriel Mountains at about 7,300 feet. The receiver site, however, was something else. One of the selected locations was in the Panamint Mountains, but how one was to get up there was a problem. So they went out to investigate to see if there was an old mining road to get to the top. The first stop was the almost ghost town of Ballarat, a town with 1 resident, well known for his prospecting over many, many years. He was an old gentleman, not just one old, but 2 old gentlemen who went by the name of Seldom Seen Slim, and very few people ever got a chance to meet him. Dave McGee and his team drove into Ballarat and ran across Seldom Seen Slim and got his cooperation, something that we later found was unusual because he avoided people and didn't like to talk. But he was a great help and told the team how to get up at least partway via a mining road, at the end of which was an old mining operation that was closed down. At this old mining operation was a guard to keep people out, but if permission could be obtained to cross this locked facility, another older road went to the top. Dave and his team went up the road, met the caretaker at the mine, and talked him into letting them pass through onto the old road. It took quite a bit of time to fill in ruts that had washed out parts of the road, but they eventually got very near the top, an elevation of about 7,400 feet with a good view toward Grassy Hollow. We eventually thought that we were ready to set up camp and try this. That was probably a mistake, as we should have spent at least another 2 weeks polishing off problems that became very obvious to us once we were on the site. My team, the operators at the receiving site, arrived at 3:15 p.m. on Friday, thanks to the owner of our company who gave us a day off, giving us a long weekend. I and my Plymouth Valiant, my wife's car actually, what was that snort from the peanut gallery? Somebody who's seen a Plymouth Valiant, presumably.
Somebody who's driven a Plymouth.
Was unable to make the last 500 feet of the very steep road. So Ron had to drag me this last distance. To her dying day, my wife never knew where I had taken it. By 3:30, we'd established the 6 and 2 meter radio links used to communicate between the 2 sites pitched our tent, and set up the telescope. I'd brought along a huge flash lamp that was mounted inside a World War II signal lamp, one of the types in which you move a handle on the side to send code. The shutter had been removed and a very large xenon flash lamp had been installed, and there was a huge power supply to run it. With that, we thought we could aim it toward Grassy Hollow and the transmitter team would be able to beam the laser toward us. When it finally got dark, we were able to sight in Park's telescope with the help of the headlights from W6 KHK's car at the transmitter site. For aiming the laser, the flash lamp didn't cut it, presumably because much of the optical power was in the blue spectrum, which was absorbed by the atmosphere. But everyone else in Southern California must have seen it. Fortunately, we had contacted the FAA and told them that we were going to be flashing this light. So they were able to pacify all the pilots flying in Southern California, and there was no problem. Failing with the flash lamp, we still had an ace in the hole, a 5 million candle power aircraft flare that we'd managed to obtain through the military. We unpacked the flare and ignited it on the ground, and for a few seconds, the transmitting site was able to see this and know exactly where to beam the laser. Unfortunately, the wind was blowing in such a direction that the smoke from the flare went toward the transmitting site, obscuring the flare itself. And they got only a few seconds of visibility, but it did light up all the terrain around us, such as the town of Trona to the west and Death Valley to the east. And many people must have wondered what on earth was going on atop the Panamint Mountains. Once we were ready to operate, they turned the laser on and attempted to beam it toward us, something that turned out to be a rather large problem. Someone in the group had calculated that moving one end of the laser assembly just 1/100th of an inch would move the beam 175 feet at the receiver site. And as it turned out, the scanning technique used at the transmitter site certainly needed some improvement. I was unaware that no attention had been paid to the fact that we needed some kind of micrometer type of adjustment on the beam, and it took a half hour of awkward scanning of the laser before we were able to see it at the receiver site. I asked Jack Pattison, who was at the transmitting site, what the problem was with moving it. We would see a flash and it would disappear. So we tried to get them to back up. But in the process of backing up, they would go too far and it would be lost for another 10 minutes or so. Jack informed me that the only adjustment they had was to tap the end of the steel channel in which the laser was mounted with a rock. When they got close, that is, when those at the receive site could see it once in a while, they switched to the fine adjustment tool, which was a smaller rock. I think that could have been improved considerably. Once we got beamed in about 10:55 p.m., we were quite aware that there were a lot of atmospheric conditions affecting the path, and the beam was fluctuating very rapidly. But that's scintillation for you. We did make some communications by laser on Friday night, but they were not too successful. Although we could understand it occasionally with signals peaking Q3, but later dropping off, we rescheduled to come back up at 4 a.m., well before sunrise, hoping the scintillation would be less with a more stable atmosphere. During the night, some winds came up and it took 2 men to hold the center post of our tent at the receiving site, with the other 4 trying to get some sleep. But that was difficult since the telescope and electronics took up the middle of the tent, causing everyone to lay up against the tent sides, with the wind blowing and tent flapping up against our backs, keeping us awake. Later that night, the winds increased and the tent came down. Murphy was working overtime. At 4 a.m., we had no winds and were back up and ready to run, but Murphy's Law struck again as they couldn't get the laser to work. By Saturday night, things were up and running again about 9:30 p.m. with a better laser signal than the night before, and for about an hour and a half, we recorded what we thought were fairly good communications, Q4 to Q5 at times, considering that we had 1/8 of a milliwatt of power from the laser over a path of over 118 miles. Again, we decided that things might be better in the morning, so a schedule was set for 4:30 a.m. on Sunday. This time, the receive site was again up and ready to go, but no one was awake at the laser site. Murphy strikes again. The first thing that you'll notice on the laser communications tape is a great deal of noise in the higher portion of the audio spectrum, and we generally played that back with the higher frequencies rolled off. I've had thoughts about why all that noise was there, but there was nothing that we could do about it at the receiving site. I think a lot of the noise was due to the resistor that was between the high voltage power supply and the photomultiplier tube, which was 100,000 ohms. And it probably was a carbon resistor, and that probably contributed a lot of noise. At least that's my theory at this time. Keep in mind, this is 50 years after the event that he's recounting this. It probably would have been much better with a metal film resistor, which at that time was available, probably for a couple years before that, and this might have reduced the noise quite a bit. Okay, so I've got some audio here. We're going to see how this works. So that's the unfiltered audio, and this one is the filtered audio. Maybe it's the other way around. I think it's the other way around, actually. We'll go back to this one. We don't have to listen to the whole thing, but I just think it's amazing what these guys were able to accomplish in 1963 with some hardware that they cobbled together, some pieces that they had laying around, some pieces that they borrowed, some pieces that they probably acquired surreptitiously from work, but that they were able to actually make this happen over 118 miles using laser light, visible actual red laser light. Pretty slick. So let's move on a little bit. When we talk about scintillation, you remember he mentioned scintillation a few times. Clint's experiments went more in the collimated LED range, but they did do some experimentation with lasers as well. But when we talk about scintillation, you might think, well, what the heck is scintillation? And Clint actually has this video that shows the comparison between laser light and an LED, collimated LED beam. So I'm going to go ahead and play this.
Here's Clint Turner's video comparing a laser beam with a light-emitting diode beam on a 24-kilometre atmospheric path. The camera is focused on the receiver's Cassegrain telescope mirror, 20 centimetres in diameter. With the laser, the speckle pattern is a chaos of deep, rapid scintillation extending up into the kilohertz region. This laser beam has a minimal capacity to convey recoverable modulation. Now the beam from a light-emitting diode expanded to 20 centimetre diameter by a collimating lens. The scintillation is slower and shallower, around 7 dB fades at 10 Hz. The beam's capacity to convey recoverable modulation is much greater than the laser, even if the beam flux is lower. Could it be that coherence is undesirable on atmospheric optical links?
Okay, so you think about that and you think, the first thing you think of, right, is the laser's got to be the way to go, right? I can get my power focused. I've got a nice, solid, coherent beam of light. I should be able to get that to go the distance, right? But what you don't understand when you think that way is this scintillation effect, which is caused by variations in the atmosphere, especially over a long length like we're talking about here. Even minor fluctuations in the atmosphere can cause that beam to shift ever so slightly. And it doesn't take much with a laser that's focused down to, 20-inch beam width. It doesn't take much to shift that away from your receiver. Whereas the collimated LED beam is less subject to that because A, it's a wider beam to start with, and B, it just seems to not be as affected by it. It seems like even when it shifts a little bit, there's still some of the beam that is still hitting the receiver. So, it can handle a lot more variation. So this was something that they observed. Okay. I'm not sure why that slide actually ended up there, but yeah, so I think that slide should have been a little later. So this is the transceiver that Clint built, and he actually built a couple of different ones. So this is the first one that he built, and you can see here, he built this like wooden box with a Fresnel lens in the front of it. And these lenses that he used were 10-inch by 12 inches. And they're about 2 millimeters thick, but because it's a Fresnel lens, it has a focal length of about 13 inches. So he was able to get significant focusing out of this beam, right? And then on his transmitter side, you can see down here in the lower left corner, this is his LED that he is using to transmit the signal, and that's mounted in one of these openings on this box. And then on the receiving side, he's got a photodiode, photoreceptor, and that's just mounted also in the same kind of position. And this picture that you can see here in the middle on the bottom is just an example of the beam as seen. It would be normally red, but this is just a black and white photo because it was used to demonstrate another aspect of the beam. But yeah, so you can see the container, the facility, or the box that he built. It actually looks pretty cool. It's got a transmitter side and a receiver side, so it's an actual transceiver. The Operation Redline guys only had a single transmitter and a single receiver, so they were only going one direction. All of Clint's experiments were bidirectional. He also built a cheap transceiver, and on this one, he used foam board to build the enclosure, and he used those little page magnifier Fresnel lenses. If you see those at the store, they're the ones that you like lay on top of the page and it makes it look bigger so you can actually read the text when your eyeballs get old. Brad, you don't know anything about that, I'm sure. But so he built one out of this, and one observation that he made was, don't let the sun shine through your Fresnel lens, because not only will it completely fry your electronics, but it even caught the foam board on fire. So that's something to consider if you're going to build one of these. He also built a third one similar to this that was made to be collapsible so that it would be easier to drag up a mountain and back down again. So, but this was his cheap version of the transceiver. So,
John,
yeah, go ahead, Dave.
I have a quick question. On the video you showed, it showed the red light.
Yeah,
It looks like it had a hole in the middle of it.
that's because it was a reflector telescope. So in a reflector telescope, you've got like a mirror on the back, right? And the beam comes into that and then is focused towards a collecting mirror at the front. And that mirror is kind of in the center of the beam. And so that's why it would have that hole in the middle.
Okay.
That makes sense?
Yeah, that's what I was going to ask, if it was
Yep.
a telescope type thing.
Yep, it was the fault of the telescope. So, okay, so this is his initial test. In this test, he only had the first transceiver available, and so he went out to on the road on the southwest end of the valley. It was Highway 111 and about 70th South, and this picture is taken from the Salt Lake City Cemetery where Gordon was positioned. And you can see right here, there's like a little dot right there. That is the transceiver site. So that's what he could see across the valley, distance of 14.85 miles. So on this first two-way test, this was March 31st of 2007, Gordon and Ron were at the Salt Lake City Cemetery, and you can see their setup in this top right picture here. They had found that there was a wall at the edge of the cemetery that was at just the right spot for them to aim their stuff where they wanted it to go. You can even see a headstone sticking up over here on the side. And then Clint was over on Highway 111, and he had set up out here. And one of the things that he notes was when he was doing this, the ground was a little muddy, which actually helped him because he used a mud-based adjustment of how high his unit was and what direction it was pointed. So by pushing down a little bit on the table leg, you could get it to sink into the mud a little bit and get the beam to go up a little bit. By pushing on the other end of the table, he could get the beam to come back down a little bit. So he said the mud was actually helpful for him. But this was their initial test. And you can see this was basically the shot. So from the Salt Lake City Cemetery up here in the kind of northeast section of the valley down to Clint's location. And so this is some audio from that. This is unfiltered here.
Hello there. Hello there, do you hear me? Yeah, I do. Let's see, I don't have my microphone on right. Hang on. Okay, here we go. I'm getting quite a bit of racket from Carl. There's a light up, there's a turn on and off that I can hear. Yeah, right here, we don't have too much, but we just got kind of.
We'll play that again with the filtering.
Well, okay, I'm gonna shut down here. Okay. All right, things are on. I'll punch on the radio. Yeah. Okay. On the DC band. Yeah, much more. Yeah, you know, we are hurting our herds like crazy here. Oh yeah, Mark would steal calls. Yeah, that's right. Okay. We brought out, we have certainly used more cycles tonight than we have in our entire previous career in radio. Yeah, in our previous lives combined. Yeah. Okay.
All right, so it actually worked pretty well.
You know what that hum is? It was duplex.
The hum is the light from the city. Yep. And there was also, it was remarked on that when Clint was listening, he could hear, like when an airplane would go by, he could hear the strobe of the airplane as a click.
Yeah.
And so as the plane would go by, he'd hear this as the plane was flying along. And then Gordon commented about a street light that was in the throes of failing. And you know how they do that where they'll turn on and then after 10 or 15 seconds, they'll turn off again. And then 30 seconds later, they'll turn on again. And so there was a street light in his vicinity that was doing that. And he thought that was causing some interference with the signal. Clint said he couldn't see it from where he was, but it was definitely, you know, a factor in the received signal on the cemetery side. So pretty cool. So observations that they made, aiming was critical, focusing and alignment also critical, lots of noise picked up from random sources. In moonless conditions, the beam itself was actually visible in front of the transmitter for several feet, probably because of dust in the air. And they also commented that at Clint's site, when a truck went by, it would stir up a cloud of dust and you would hear that scintillate or that dust factor and reflection from the transmitter back into the receiver on his local site. So he would actually hear his own audio bouncing off of the dust from a truck that had gone by. And then as the dust would settle, that would fade. So pretty darn cool. They figured out that the cheap enclosure performed just as well as the fancy enclosure, even given the fact that it was using, you know, 99-cent book reading Fresnel lenses instead of the fancy scientific ones that Clint had in his big unit, in his main unit. So, but yeah, pretty cool. Got about, what did they figure, about 14, 15 miles out of it. So their second test, they set up again. They had made some modifications of things. They had done a little bit more planning and adjustment. They tried both an LED light source and a laser source, and they also tried just a spotlight that they could turn on and off. The laser was much more subject to scintillation. Aiming was facilitated by doing some additional work on the mounts. So they actually added better control so they could adjust, make very fine adjustments to the angles that the systems were mounted at so that they could control the aim a lot better. And they often heard clicks from aircraft going by from their strobes. There was one actual recording where Clint pointed the receiver at the Bacchus refinery site, you know, the big smokestack at the north end of the valley there, at the north end of the mountains. And he could hear a definite pulse every time that happened. And he actually recorded that and analyzed the audio and saw that strobe pulse was actually 3 separate pulses. So there'd be a pause and then there'd be tick, 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 and then a pause and then tick, tick, tick. And so that whatever those strobes are made out of, the way they turn on, that would be the effect that he was seeing. So kind of interesting. Either that or there were 3 strobes that were ticking off just slightly altered from each other. I don't know. His assumption was it was something about the strobe. I think it's more likely to be that there are 3 of them mounted on that towers.
You know, sometimes on a light like that, they'll intentionally blink it, pulse it multiple times just for a long duration flash, because your eye can miss one.
Right. So it could be a combination of the two. So their second test was done on April 25th, also very successful. So then they thought, okay, let's go for a long distance attempt. So they set up the north end at Inspiration Point, which is near Willard Peak in the Ogden area. And with the south location along the Nebo Loop, south of Payson. They had Ron, Elaine, and Gordon. Elaine was Ron's wife. So Ron, Elaine, and Gordon were at the north location, and Clint and Tom were at the south location. They figured out they had about a 107-mile path, and the weather was not cooperating. And if you go on the site, and I'm going to give you the link to the site at the end of the presentation, but if you go on the site, there's a lot of commentary about getting to these sites, because some of these places that they had to get to were non-trivial to get to. And not only were they non-trivial to get to in daylight, they were definitely non-trivial to get away from in the middle of the night. So it's quite interesting and quite an amusing read. And definitely you should check it out on your own time. But yeah, so the weather wasn't cooperating. There was rain, there was lightning in the Salt Lake Valley. They still managed to get a link up and working, even with all of these problems. So here's the signal with no noise reduction on this side. I'm not going to play any more of that because it's just as bad all the way through. And then this is the one with the noise reduction. Just as good, isn't it? But you can barely make out, you can kind of make out what they're saying. You hear those pops and rumbles. Those are caused by extraneous things in between them that are lighting up, right? Anything that's causing light to happen. So remember, they're shooting right over the Salt Lake Valley. So they've got the entire Salt Lake Valley in between them. Not necessarily the best spot for this kind of a test, but 107-mile path, they were able to get it to work. They were able to actually communicate over this link. It was pretty darn amazing. They tried again on September 3rd. The weather was much better, much more cooperative. This time they had made some modifications to the transceivers to reduce crosstalk. They found that when both the transmitting side and the receiving side were running from the same battery, there was some crosstalk between the two. And by splitting that out and running a separate battery for each side, the transmitting side and the receiving side, and adding some shielding in between the two, they were able to clean that crosstalk up quite a bit. So we've got a little bit of audio here. That music that they sent was opening bars from the movie Dark Star. If you guys have never seen it, don't bother. Somebody has seen it. Yeah. With the bomb. I love the bomb. Oh, I'm gonna blow something up. Oh, not yet. Oh. Yeah.
And he said that people didn't get it.
People didn't get it. Yeah.
So he decided if he couldn't entertain that way, he would scare them next time.
Isn't it still against the rules to transmit music using light?
I talked to Clint about that issue.
I was going to ask about that because I thought the same thing. I'm like, what are they doing? Sending music over this link? What are they doing here? Go ahead. What did he say?
There's a gray area about whether or not this is amateur radio, because you could conceivably do these experiments without any license at all. So,
So even though they were using amateur radio to coordinate things, they weren't necessarily doing amateur radio with the actual transmission.
I've been tinkering with the idea of using an infrared beam to link between two repeater sites. And so I was interested, well, do I have to put an ID on that link?
On that link.
And I think what it comes down to is, if you're going to use it for something that requires amateur radio, the FCC says an auxiliary station has to be licensed and everything for links between repeater sites. Then you use your call sign, you put timers on it, just like you would any radio link, you call it a radio link. But if a hobbyist builds this and goes out without an amateur radio license, technically they're not illegal. So
Interesting.
it's a gray area.
Yeah, I would have used something other than music, but you know, and they did use other things other than music. We'll talk about more in a bit. I'm gonna go ahead and finish playing this.
All right. Hello, how are you? Oh, okay, let's see, how's that?
So this recording is the one link on one audio channel as it's received, and the other is the other link as it's received on the other end, and they've just put the two together. So you can hear both sides, but both of these are post transmission via light. So
Okay, well, it's probably, oh, anyway. What are the grist first? You remember?
ID, right?
I think it's. You are Alpha Delta Nancy 41 Alpha Japan.
Okay, so not bad. I mean, very copyable, over 107-mile link over the Salt Lake Valley. Admittedly, dark night, good weather, no rain in the middle or anything like that. But yeah,
A lot of noise coming from the Salt Lake City.
a lot of
area.
noise,
Phenomenal.
a lot of noise. So this was their second 107-mile attempt, and this basically redid essentially the transmission like the guys in California did 50 some odd years earlier. Okay, so now they wanted to do a longer shot. They wanted to try to break the record, right? And so they thought, well, let's figure out a path that we can work with. And they identified a path from George Peak in the Raft River Range, which is right close to the Utah-Idaho border, and Swayze Peak, which is about 70 miles west of Delta. So this is a 173-mile shot. And that's a long distance, right? Getting everything ready was, they spent like 3 days getting everything ready before they even made the attempt. And then on September 15th, they drove up there and tried to get it set up. And they were not able to see the other end of the link at the time. They did set up some Yagi antennas pointed at each other, so they were able to actually talk back and forth on 2 meters. And they were able to successfully point the Yagi at the 6.2 repeater on Farnsworth and have a conversation with somebody in Ogden at the time. So that was kind of cool. But yeah, so they were out there and it just didn't quite work. They were not able to get any visual connection between the two sites. So they tried it again on October 3rd, 2007. The South team was Ron, Brett, and Gordon, and the North team was just Clint by himself. And ultimately, they were not able to establish two-way voice contact, but they did successfully send modulated CW and regular CW by switching the light on and off. And they also were able to send, well, I'll show you the pictures. But we're going to run through some of the audio first, and you can hear what this sounded like. So this is on that 173-mile link, right? So this is just a straight tone being sent from Swayze to George Peak. Remember, Swayze is at the south end by Delta, and George Peak is up by Idaho. They could actually hear that tone, right? They were able to hear that. Then they sent a 1 kilohertz tone from George, and this is what it sounded like at Swayze. So that's pretty solid, right? I mean, that's not too shabby. So they were able to send, so you guys know what MCW is, modulated CW. It's basically taking audio, putting, like a CW signal on an audio signal, not a real continuous wave transmission, but where you, like when the repeater IDs, that's an MCW signal. It's not real CW. They're not like turning the repeater on and off while they send that. It's just modulated into that signal. So they were able to send some modulated CW. That's without filtering. Let's listen to it with the filter on. So that's pretty solid, pretty copyable, right? And then this is the opposite direction. And again, that's copyable. It's pretty low. It's down in the noise there, but you can copy that signal. And so that's all they needed to do. They successfully made a connection over 173-mile length. Now, they did try to do some voice as well. This was the unfiltered voice. You can kind of hear the voice in there, but you can't really copy it, right? And then you also hear those weird thumps in the background too. And that's got to be something that they said later they couldn't see what was causing that, but they figured there must have been a light source somewhere that was periodic that was tripping that out, and they were picking that up. So this is that same signal filtered. And again, you can almost make it out. It's like you can almost copy that, right? But just not quite. So they didn't consider it a successful voice communication. They did send some slow scan TV, and the way that they set this up, they actually recorded the slow scan TV signal. We talked about slow scan TV before. It's basically a way to take an image and encoding it into an audio signal.
It's a fax machine without paper.
Exactly. So what they did was they took the initial picture that they wanted to send and they encoded it and recorded that sound. And then they took the recorder up with them rather than actually trying to send it live. And then they played the audio from that. And you can see the difference. This is what was sent on the left here. And then this is how it was actually received. So pretty crappy, but you can almost make out Clint's fabulous shape here in the devices in front of him. And then on the return signal, you can make out the line pretty well, but that's about it. You can't make out any of the text. Now, if they were to have dressed this up a little bit, maybe sent it several times. Yeah, right. Big font. Sent it several times. They may have been able to get that to actually come through in a legible fashion, but in general, it was not considered successful in the attempt to send slow scan TV over that. But I think it's pretty cool that they got to work what they got to work, right? So the results, it works. The clarity of the air matters a great deal. The quality of the lenses isn't that big of a factor. Having an RF connection is critical to getting the aim right. If you read through their description of the process, they're talking through like, oh, yes, I can see it now. Oh, nope, I can't see it anymore. Come back the other way. And just like the things that were talked about from the 1963 experiment, where they were saying, you know, a very minor adjustment hitting the thing with a rock was enough to move the beam 175 feet on the other end, right? So these are things that you need to think about. Having that kind of way to communicate out of band from the video or the visual signal was critical. They had binoculars, they had telescopes set up so they could actually see the other end and see, oh yes, I can see your signal now, I can see your beam. So I know where you are. I'm going to try to point my stuff at you. They thought about some things like if we added like a spotting scope to the transmitter so that they could narrow it in better as far as where it was aimed. That might have helped. If they had finer controls, like vernier type controls on the aiming, that probably would have helped them target it in better. Scintillation was a huge factor. Any noise in the air, any disruptions in the air would just knock the signal all over the place. Lots of noise from other signal sources. You heard those thumps. That was probably things driving down I-80 in between the two sites, right? Like vehicles driving down I-80, you'd hear like a thump go by as, you know, a light went through the beam or something, right? So all things to think about as far as doing this again. I don't think they've done it again or tried to do it again since 2007. But when I first read about this, I thought, you know, okay, it's kind of cool. But now that I've really gotten into it and read about it a little more and thought about it, this would be fun to try. Just to be able to do it, right? Even if we only did it from one end of Murray Park to the other, it would still be freaking cool to do it. Don't you think?
Clint told me that doing this with the equipment improvements that have occurred since 15 years ago would be trivial, that this would be easy to do.
Yeah. What kind of equipment improvements are we talking
Well,
about?
more powerful LEDs.
Yeah.
More sensitive photodiodes for detection.
I think it would be fun to try it. I just do. It's just goofy enough that it would be fun to try it. And you know, it's one of those things where a couple of guys were sitting around probably at Lisa's Pizza after the club meeting at UARC, yeah, and said to each other, huh, I bet we could do this. Oh no, that would never work. Oh, I bet we can. I'm going to try, right? Yeah, challenge accepted. So yeah, I encourage everyone to visit Clint's modulated light pages. It's www.modulatedlight.com or .org. Either one will work. There's a ton of information there that I did not include because I didn't want to sit here and read everything to you. There were also some other topics that we didn't talk about. We didn't talk about heliographs. We didn't talk about signal mirrors. We didn't talk about fiber optics. We didn't talk about space lasers.
We're not Jewish.
Well, okay. Some of us maybe, we don't know that. But yeah, so those are things that we didn't talk about. The heliograph was basically, heliograph and signal mirrors have a lot in common with each other. The idea being you have a ray of light from the sun hitting a mirrored surface, and you can aim that mirrored surface at where you want to. So just like the Navy signal light, you can put a shutter in front of that heliograph mirror as well and turn that beam on and off. And that can be seen long distances away, right? Signal mirrors, I used to have one. I don't know where it got off to, but 30 years ago, I had this little mirror, and it was just a mirror about maybe 2 by 4 or something like that. It had a hole in the middle of it. And there was like a little wire grid mesh in that hole. And that was instrumental in aiming the mirror. And what you would do is you would hold this mirror up so the sun was shining at you. And then you'd look through the hole and you could actually see a glowing spot that was indicating where the mirror was beaming its signal to. So you could put that spot on a group of people or a vehicle or an airplane or something and be able to signal them. But you could modulate that by moving it away from them and moving it back to them, right? So you could send Morse code signals through this signal mirror. Super amazingly handy to have. It weighs like 3 ounces. You can stuff it in your backpack. If you're out in the middle of the boonies somewhere and you can't get communications to anybody, but you see a plane flying across 30 miles away and the sun is over there, you can signal them.
And the pilot knows.
And they will see you. Trust me. It's bright enough that the sun is bright. It's bright enough that they'll see you. Fiber optics, we use fiber optic communications all the time. We use them for transmitting signals. Fiber optics are great because they eliminate that whole scintillation problem. There's no atmosphere in between the transmitting laser and the receiving receptor. The Elon Musk's Starlink satellite system, his plan is to use lasers to communicate between the satellites. And that won't have the scintillation problem because no air in between them. So you'll have a nice, tight, well-collimated laser beam that is, a nice coherent laser beam that is able to carry a signal quite a long distance in space. But that's all I got. I thought it was cool.
You know, if you go to Clint's website, modulated-light.com, make sure you've got some time,
Yes,
because it's a rabbit hole that's
there is,
crazy fun.
there is a ton of, of text on there that talks about, and then we drove up the side of the mountain and discovered that there was still snow there. And the Jeep didn't want to go that way, and, you know, things like that. It's a really good read. It's definitely worth spending some time with. When you have some time, get on that site, check it out. Lots of cool stuff. Yeah, that's all I got. So thanks everybody for coming. And I'm gonna stop the recording.
You know, if you want to